Hi everyone, Mr. Smith here. In this video lesson, we're going to be not really learning any new concepts related to electric forces and fields, but we're going to do an application specifically that involves parallel plate capacitors, and that's inkjet printers. So it shouldn't take too long. We're going to walk through two examples. It should be fun. So let's get started. So kind of just saying this in a simplified way, the way an inkjet printer creates images or letters or characters, it involves squirting drops of ink from a nozzle that's moving rapidly back and forth. And the pattern is controlled by a valve that determines, so when a nozzle is in a certain position, whether the ink is squirted or not. And the ink can be squirted at an angle or a deflection depending on what the charge on the parallel plate is that it's fired through. So here's what I mean by that. So imagine we have a parallel plate capacitor. And here this D sub 0 is like how long the capacitor is. So it's how long an ink droplet will be, like the distance it travels while it's between the parallel plates. So we have a parallel plate capacitor with a certain electric field. So that's capital E in the diagram, but it's like epsilon. And it's a charge droplet. So if you've seen like a spray bottle or like an atomizer, when you use a spray bottle and create those fine droplets, often the friction involved in creating those fine droplets actually puts a charge on some of the droplets. So in the same way, you can get these fine ink droplets and have a charge on them. And so this ink droplet has a positive charge. And when it enters into these parallel plates, where we have an electric field from the positive plate to the negative plate, and you can see it's going up, this charge is going to experience a force, and that force is going to be equal to the charge on the ink droplet times the electric field strength. And because it will experience a charge, it's going to accelerate. And as it moves through the parallel plates, it's going to have that horizontal component of constant speed, but it's going to have some kind of vertical acceleration, and it's going to accelerate up and up, and its trajectory will curve along the blue line like this. And by the time it leaves this parallel plate, it will have been deflected a certain amount d, and the ink droplet will fly off on the page. So by allowing for these deflections, you don't need to have a setting for a nozzle to be at every position. So a nozzle at one position could deflect an ink droplet different ways to make the printer more efficient. So we're going to do two problems with respect to a setup like this. So in our first problem, we're looking at an ink droplet with a mass of 1 × 10 to the negative 11 kilograms. So it enters it leaves the nozzle and goes through this parallel plate capacitor at 16 meters per second. And they pass through this charging unit, this parallel plate, and this causes it to lose some electrons, and so it gains a charge, and now it's going to be deflected through these plates. So we're given the magnitude of the electric field between the two plates, and with that, we can determine in this case, we're going to determine the deflection. Didn't actually say what the question is for example 1. That's okay. We're going to improvise here. Keep my annotations. Inkjet problems. We're doing this guy. Make a bit of space. And we'll screen grab this guy. Here we go. I was reading the question, like, where's the question? You don't actually see a question. Okay, well, now we're good. And I'll just actually copy that to my next screen too. All right, we're back in business. definitely not worth restarting the video for that. Here we know we want a certain deflection. We want this deflection to be 0.32 millimeters by the time it reaches the end of the plate. So what we have to figure out is we're going to figure out what the charge on the drop has to be in order to have that deflection. So let's begin. I don't actually think I use the density in this problem. In an older version of this problem, I might have done that, but I don't think we'll need it. So let's get started with a solution. Use yellow, show up good in the black here. So first thing is we can actually calculate how long the ink droplet is inside these parallel plates because we know the distance it travels and we know the speed it's traveling in that horizontal direction, right? We're told that the plates have a length of 2.5 centimeters, so 0.025 meters, and they go through at a speed of 16 meters per second. So let's just actually crank that out. And I might keep all the accuracy here just for moving forward in the problem. So it's only in here for a very short time. It's like 1.5 milliseconds. So we know how long it's in there for. So the second thing we want to look at its deflection and its acceleration in the y direction. And I want to actually just do something aside with you guys. All right, so we want to find the vertical acceleration so that we can use the fact we know the deflection to work backwards and find out what the charge on the drop is. So what's the force acting on this charged ink droplet as it's going through? Well, it's the electric force. And if you recall, in our lesson on electric fields, we had an expression for the electric force. It was kind of like Fg equals mg, but it's for electric force, right? And it was this. It was force equals the charge in the field times the electric field strength. And in our problem, remember, with parallel plates, the electric field strength is constant. So I can rearrange this and I can get an expression for the acceleration in terms of the charge, the electric field strength, and the mass. And that's good because in this problem, there was two things we really didn't know. We didn't know the acceleration and we don't know the charge, but now we have the acceleration in terms of the charge. Now let's look in so we've found the time. Let's look at the motion in the y direction. And I'm going to set up this kinemax equation in the y direction, delta dy equals v1y delta t plus 1/2 a delta t squared. Now, when the ink droplet enters the parallel plates, what's its vertical component of velocity? It's 0, right? Because it's moving horizontally through. That's great because we actually know delta dy. I'm going to replace that. That's our d, right? Equals 1/2. And we found an expression for a. It was q epsilon over m times delta t squared. And if I think about it, I know everything in this equation here except for q, so I can solve for it. So I'll take the 2 and the m on the bottom and multiply them up. So 2md. And I'm getting q by itself. So I have an epsilon and delta t squared I have to divide out. And this will get us the charge required to have that specific deflection. So the mass was 1 times 10 to the minus 11. The vertical deflection, we were told, was 0.32 millimeters. So 0.00032 in meters. And the electric field strength, 8.1 times 10 to the 4. And we found the time that the drop is traveling in there to be about 0.0056 seconds. So we have everything we need. Let's find this charge. Point 0.00032 x4 and divided by 0.0015625 squared equals. Right, so I got about 3.24 times 10 to the minus 14 coulombs. So I'm going to double check because I got 3.28 the last time I did this problem. 0.1. No, everything seems pretty good. Yeah, we'll just go with that. So that's the charge on a single droplet. If an ink droplet has that charge going in, it's going to experience a certain force that's going to give it a certain acceleration. And within that time, it's in the parallel plates undergoing that acceleration. It's going to deflect vertically a distance of d, which in this question is 0.32 millimeters. And it will land in a very specific spot on the page. So if we know what charge we need to give it, then we can, engineer and build our inkjet printer to provide that certain charge to get the deflection we want. I'm going to just do a second type of problem with this. So in this case, we have a second droplet with a certain charge, and it's fired with the same horizontal speed into the plates. And we're going to find the deflection. So now we saw with the charge of 3.24 times 10 to the minus 14 coulombs, it deflected by 0.32 millimeters. What will the deflection be for a bit more of a charge? Well, let's find out. So some things are actually the same with this question that we don't really need to redo. For example, Vx, same speed. And because it's the same speed and the same plates, we're going to use the same time, 0.0015625. It's the same as the previous question. Also, the expression we got for the acceleration, we don't really need to rederive that. We're just going to make use of that again. And so this is all from example 1. Like we don't need to redo all that. We already did it. So here we go with our question. We're going to again analyze things in the y direction. So delta dy equals v1y delta t plus 1/2 a delta t squared. Again, v1y is 0. That's nice. And I might actually just refer to that as d, like we have in the diagram. So d equals 1/2. Again, replace acceleration with q. And then delta t squared. So instead of solving for q in this one, we have q, and we want to calculate this vertical deflection. So let's go ahead and do that. So we have 1/2 6 times 10 to the minus 14. The electric field was 8.1 times 10 to the 4. The mass was 1 times 10 to the minus 11. And the time, 0.0015625 squared. Yeah, so for this one, we're actually just able to calculate the deflection. So that'll give us d, and we'll be done that part. And 0.0015625 squared equals okay. So I got 0.00059 meters, which is about 0.59 millimeters. So that's our deflection there. And now we're asked to find the speed and the angle that the ink drop leads the plate. So that's going to have that velocity is going to be at an angle to the horizontal, right? And right now, all we need to know is Vx. So let's find V2y. So what is the vertical component of velocity for that ink droplet as it leaves the printer? So V2y equals V1y times A delta t. Now remember, V1y is 0, and we actually have our expression for A was Q epsilon delta t over M. Six times 10 to the minus 14, 8.1 times 10 to the 4, 0.015,625. Mass of the droplet, 1 times 10 to the minus 11. And I got about 0.76 before, but I'm in the habit of double checking these. 8.1 x 4 times 0.0015625. 11. Yep, about 0.76 meters per second. All right, so let's put those together. So what we know is that the ink droplet is moving with the horizontal speed of 16 meters per second. And we just found out that as it leaves the printer, or the parallel plates here, it has a vertical component speed of 0.76 meters per second. That means we can find the angle and we can find that final speed that it leaves with. So that's just right angle trigonometry. So I'm running out of space, so I'll leave the details to you guys. But Pythagorean theorem, 16 squared plus 0.76 squared, and then rooting that, should be pretty close to 16. Yeah, it's essentially 16. It's like a tiny bit faster. I mean, the sig figs is the same. It's like 16.02 meters per second. And what's that angle of deflection? It's not going to be massive because it's a printer, right? I mean, the paper going through, it's not very far away. You don't want it to be deflecting a whole ton, but let's find the angle. 0.76 divided by 16, and then shift tan. So yeah, pretty tiny angle, and that's 2.7 degrees above the horizontal. So I thought that was fun, a little cool application of making use of parallel plates and making use of the fact that when the electric field is uniform, like it is in parallel plates, the force on a charge, and hence the acceleration, is constant as well. And then we can use our kinematics equations, our 2D motion skills to actually solve some problems in a practical sense. So I thought that was pretty fun. And that actually brings our day to a closure, at least if you're taking my online course right now. We have kind of finished talking about electric forces and fields. And the next step, what we'll do in our next day of lessons, is take our comparison to the next level with gravity and talk about electric potential energy versus gravitational potential energy. Because, just like it would take work to pull two masses apart because they're gravitationally attracting each other, it would take work to pull two opposite charges apart. So if you're pulling two opposite charges apart, we're storing some energy. But unlike gravity, charges can attract or can repel too. So I would have to work to push two charges together. So instead of having two different formulas, we're going to talk about how that works and how we can calculate electric potential energy. So it should be interesting. That's it for now. Hope you guys are staying well. Have a great day, and we'll see you soon.